What's going on? What's going on? So, you've seen the title. I'm speedrunning probability and statistics because I have a final coming up and I'm relatively prepared, but this is the start of my real studies, so I'm just gonna run through all of the lecture notes and try to get a broad overview of all these concepts into my mind, how they line up together. I'll do the actual problems later, but for now, I'm just gonna speedrun everything. So, if you ever wanted to get a Northeastern education in probability and statistics, this is your chance. So I'm just gonna jump in, run through this stuff. This is probably not the best way to learn if it's your first time, but here we go. So sample spaces and the algebra of sets. Basic terminologies. You have experiments, you have sample outcomes, a sample space with all the events that could possibly happen. Probability of an event is number of ways it can happen over total number of all possible outcomes. Think about a two-sided coin. Probability of heads is a half because there's one head and there's two outcomes, right? So, okay, same logic, just but with cards. You have the definition of sets and elements. You have sample spaces, cardinalities, just the number of stuff in the sample space, blah, blah, blah. You could think about events and sample spaces in terms of Venn diagrams. If they overlap, that's the intersection. If they don't overlap, they're mutually exclusive. And the A and B together here, all of that is the union of A and B, right? And so here we go. Complement, everything outside of A is A's complement. De Morgan's law, A union B complement equals A complement intersect B complement. And likewise the other way, you just have to invert the union versus intersect sign. And this is De Morgan's law visualized, right? And so, okay, yeah, this is just proving some stuff. And good thing to note here is that the die has 6 faces, and if you toss it 4 times, the size of the sample space is going to be 6 to the 4. It's a good little heuristic to know. You have the number of possible outcomes raised to the power of the trials. And cool. All right, the probability function. So sample space, event. The probability of an event is probability of A is the cardinality of A over cardinality of S, just the number of A's over the number of S's. So if we're rolling 2 6-sided die and we have one red, one blue, and we're looking for an event A, which is the difference of the absolute value of the two numbers is 1. These diagonal lines are all of the events for which that is the case. And so the probability that we get this case is 10 out of the total 36 possible events. Now we have Kolmogorov's probability axioms. I'm just going to talk about this mutual exclusivity one because the others are, well, these two are straightforward. Probability of A union B, if they're mutually exclusive, which means no overlap, is just the probability of A plus the probability of B. And then this is just extrapolating that to more than 2 variables. So remember in Kolmogorov's definitions, conditions of equally likely and finite are not needed anymore. So yeah, this is thinking about countable sets. Getting ahead with no more than 3 tosses. You could think about this as the sample space, or you could think about this as the event space, I guess, the set for which these events will, this constraint will hold true. And theorem 1, probability of A's complement equals 1 minus probability of A. Simple enough. Just remember, if you think about a circle in a 2D plane, everything outside of A, the circle A, is the complement. So, and the sample space has to equal 1. So 1 minus the probability of A gives you everything not in A. And then the probability of the empty set is 0, straightforward. If A is a subset of B, then the probability of A must be less than or equal to B, right there. And for every event A, we have probability of A is less than or equal to 1, again, because the whole sample space has to be equal to 1. The probability of the sample space. Theorem 5, probability of A equals probability of A intersect B's complement plus probability of A intersect B. So simple enough, you have A and B here. B's complement is everything not in B. And A intersect B is this right here, this sliver. So A is just the part of A that overlaps with B plus the part of A that does not overlap with B. And then probability of A union B equals equals probability of A plus probability of B minus probability of A intersect B. And the way to think about that is if you didn't subtract the A intersect and you counted A and you counted B, then you'd count this overlap twice. So you have to subtract out the overlap to have the real probability of A union B. And then these are examples. Draw 2 cards from a standard deck. What's the probability that the first card is larger than the second card? Think about that. Well, the deck has 52 cards. We're drawing 2. So the first time you draw, you could get anything. So 52 over 52. And then the second time you draw, you want to make sure that you only considering the cases where that first card was larger than the second card. So let's see here. How did they do it? Probability of C equals 52 over 52 times 3 over 51. 1 equals 2 probability of A plus 3 over 52. 3 over 51. So the first is anything. The second could be, in my logic, I'm thinking it could be almost anything. Let's see here. Let's just read it out. A is the first card is larger. B is the second card is larger. Okay. C is the number of the first card equals the number of the second card. I see. Okay. That makes sense. So A, B, and C are mutually exclusive, right? And then the sample space is A union B union C. 1 equals the probability of S equals probability of A plus the probability of B plus the probability of C. So the probability that the first card is larger plus the probability that the second card is larger plus the probability that they're equal make up the entire sample space of outcomes. And by symmetry, number in A is equal to number of B. That makes sense. So probability of A is equal to the probability of B. And then the probability of C equals 52 over 52, because that first draw could be anything. And then there's only going to be 3 cards remaining out of the remaining 51 that could equal that first card. Okay, so this makes sense. And so that then we have, so probability of C is 3 over 51, because 52 over 52 is just 1. And so the whole sample space 1 is 2 times the probability of A plus 3 over 51, and you're going to get 24 over 51. And again, that's the probability that the first card is larger than the second card. So the trick there is really just enumerating what the possible events are and then doing some addition once you realize that these possible events make up all the possible events. Cool. So speeding through some of these other examples, counting and probability. For a finite sample space with all equally likely outcomes, it is still very important to use the classical definition of probability to compute classical examples. A very basic principle of counting is the multiplication rule. If operation A can be performed in m different ways and operation B in n different ways, the sequence, operation A, operation B, can be performed in m times n different ways. Makes sense. A very intuitive way to grasp this is with these trees. So the number of ways to arrange k objects of a set in n distinct elements, permutations, in a specific order, repetitions not allowed, is denoted by the symbol n permute k, or these other symbols, permutation nk, and it's just n factorial over n minus k factorial, but I don't really need to know that because I can just calculate that on a calculator. But the idea is just that you use the permutation to find the number of ways to arrange k objects of n distinct elements in a specific order. So permutations are ordered arrangements. And yeah, this is an example. NBA. What's the probability that we get the word NBA if we arrange these letters, A, B, and N randomly? 3 is the N here. We have 3 distinct elements, and we're arranging 3 objects. So 3 permute 3, and we're going to get this. So, and this logic is just expanded upon here. Looks like they're bringing in combinations here. So how many ways can we choose a committee of 3 people? So when order doesn't matter, you use combination instead of permutation. And the number of ways to choose a subset of k elements from n distinct objects, combinations, without regard to order, is n choose k equals n factorial over n minus k factorial of that times k factorial. Now, some more examples of this, but we're good. We did it, guys. We made it through. Should I talk about hypergeometric probability? I think that's coming up in the next section. So let's just go to the next section here. So, conditional probability. The conditional probability of an event A in relationship to an event B is the probability that event A occurs after event B has already occurred. So, given the condition that event B has occurred, what is the probability of A? The notation for conditional probability is probability of A given B. This notation does not mean that A is divided by B, rather, okay, blah, blah, blah. Definition of conditional probability, probability of A given B equals the probability of A intersect B, so this overlap right here, divided by the probability of B. So this entire B right here is going to give you the probability that you get A given that you know you're getting B. And the way that you can think about this division operation is it's sort of zooming in from the universe of S into the universe of B. That's why we're dividing. Okay, when we calculate probabilities involving one event and another event occurring, we multiply their probabilities. In some cases, the first event happening impacts the probability of the second event. We call these dependent events. In other cases, the first event happening does not impact the probability of the second. We call these independent events. So the multiplication rule, for any two events, we can say that probability of A intersect B equals the probability of B given A has occurred times the probability of A occurring, which is also equal to the probability of A occurring given that B has occurred times the probability of B. Note, here are some examples of dependent events. Drawing a card from a deck and not replacing it, and then drawing a second card. Okay, straightforward. Maybe let's just go through this example here. 3 cards are drawn from an ordinary deck and not replaced. Find the probability of these events. 1, getting 3 jacks. So the probability of getting 3 jacks is 4 and 52 on the first draw, 3 and 51 on the second draw, 2 and 50 on the third draw. So you multiply these together, and now you've got the probability of getting 3 jacks. Next, getting an ace, a king, and a queen in order. So there's 4 aces on that first draw out of 52, 4 kings out of 51, 4 queens out of 50. Multiply them up, and you get that. So straightforward. Let's go to this example 5 here. Urn 1 oh yeah, there's some stars on it, which means it's probably good to remember. Urn 1 contains 2 red chips. Okay, you got an urn, you got 2 red chips and 4 white chips, so we can visualize this right here. Urn 2 contains 3 red chips and 1 white chip. That's urn 2. A chip is drawn at random from urn 1 and transferred to urn 2. If a chip is drawn from urn 2, find the probability that the chip drawn from urn 2 is red. So the way you could think about this is there is a 2 out of 6 chance that the chip drawn from urn 1 is going to be red, which means there's a 2 out of 6 chance that urn 2 has 4 red and 1 white. And there is a 4 out of 6 chance that urn 2 will have 3 red and 2 white. Okay? So you're going to want to multiply 2/6 times, which is just 1/3. So 2/6 times 4/5. And then what are we looking for again? Find the probability that the chip drawn from urn 2 is red. So 2/6 times 4/5 plus, yes, plus. I cheated a little on that one, but plus, it makes sense. Plus, what is it? 4/6 times 3/5, and yeah, that's what it is. You could draw it out, or you could do it in your head, or you could cheat a little bit like I did. Bayes theorem, pretty important thing. Let me zoom in a little bit here so it's a little bit more clear. There you go. Now you can learn too. Oh my God, no, that's too much. All right, Bayes theorem. Yeah, so let A1, A2, AN be a sequence of events such that the sample space is the union of all these events, and they're all mutually exclusive. There's no intersections. Then for any event B, probability of AJ given B. And to simplify this, you can also just not make it N events. You could just make it 2 just to simplify it. So just for pedagogical reasons, I'll just say the probability of A given B equals probability of B given, oh, okay, they got the sum in there, so forget I said anything. Just read this. The probability of AJ given B equals probability of B given AJ times probability of AJ, right? So this is that same operation we were thinking about up earlier when we were talking about the multiplication rule. Probability of A intersect B equals probability of B given A times probability of A. But now that is our numerator, and our denominator is the sum from I equals 1 to n of probability of B given AI times probability of AI. So just to sort of rephrase that, the probability of an event AJ given that an event B has occurred is the probability of that event B occurring given AJ occurring times the probability of AJ occurring divided by essentially the probability of the intersection of B and all the other events, because it's mutually exclusive. And if that didn't make any sense, a good way to think about it is that B is taking up this whole space, whereas all the A's are mutually exclusive, so they don't overlap. So if you want to find the probability, let's say, of A1, given that you know B occurred, then you're going to want to find the probability of B occurring given that A1 occurred. So this little sliver here times probability of A, because we're just thinking about this part right here. And then divide all that by the probability of B given all the rest of the stuff times the probability of those. So it makes sense that it would be pretty small when you're looking at that. And all this stuff, oh my gosh, all this stuff is going to be a lot more probable. And a real straightforward English way of thinking about it is that the product of branch probs leading to B through AJ divided by the sum of products of branch probs leading to B. Okay? So we will speed run this stuff. Maybe I should read off one more example. I'm not going to read the Monty Hall problem because this is not the movie 21. Example 7. A computer manufacturer uses chips from 3 suppliers. Okay? Based on past performance, she knows that the chips from supplier A will fail with probability. Okay, to be honest with you, I know this is simple. Just, you can pause the video if you want to figure it out for yourself. But this is a speed run, and so staying true to my word, let's move on to 2.5, independence, after a little sip of coffee. Okay, so just going straight into examples here. Roulette wheel. A roulette wheel has 18 red, 18 black, and 2 green. If you spin the wheel 2 times, what is the probability of getting 2 red? So R1, the first result is red. It's going to happen 18 out of 38 times. Sorry, 38 times. R2, the second result is red, which is going to happen. The second result is red. Again, there's just an 18 out of 38 chance on any given run. And then the probability R1 intersects with R2, so just the probability that you get the red on both R1 and R2, equals probability of R2 intersect with R1, so it's just symmetric, equals probability that you get the red on the first one, times the probability that you get the red on the second one, given that you got the red on the first one. But since this is a roulette wheel and the second spin has nothing to do with the first spin, it's just going to, the probability of R2 given R1 is the same as the probability of R2. And so you just square 18 over 38. The sets A and B are called independent if the probability of A intersects with B equals probability of A times the probability of B. The roulette wheel is a good example. These are independent events. And so you just multiply them together and you get the intersection. Recall our theorem, probability of A intersect B equals probability of A given B times probability of A. If A and B are not empty set, we have the following equivalent definition. The sets A and B are independent if and only if probability of A given B equals probability of A, and vice versa. So let's move through this. It is important not to confuse mutually exclusive and independence. In the above example, A and B are not disjoint. Consider event C. The card is a jack. then A and C are disjoint but not independent. Hold on. Oh, okay. They were referring to this event, A and B, not the R1, R2. So, yeah, a king could be a diamond and a diamond could be a king. So, yes, event C, the card is a jack. A and C are disjoint, right? Because a card can't be a king and a jack. But they're not independent. One doesn't imply the other. I would say they're not independent. Why? Draw a card. Are sets A and B independent? A and B are independent. So this is like a little trick, right? Because you might think that because a king could be a diamond and a diamond could be a king, that there is some dependence there, right? The probability of getting a king seems somewhat linked to the probability of getting a diamond, because 1 in 4 kings is a diamond. But when you think about it purely mathematically and seeing if the events satisfy this condition, then you're not going to rely on the intuition. You're going to actually check. You're going to say, okay, what's the probability I get a king? 4 out of 52, which is 1 in 13. What's the probability I get a diamond? 13 out of 52, which is 1 in 4. And now we need to check, is the probability A intersect B equal to the probability of A times the probability of B? And so without cheating, I'm not really looking, I'm looking at myself here. What do we need to find out? We need to, so first let's do probability of A, probability of B. We're going to get 1 over 13 times 1 over 4, okay? And that's going to be what? 1 over 52. And then probability of A intersect B is going to be probability of A intersect B, so the probability that king intersects with diamond, which is again 1 over 52. So when we make this check, we find that the probability of A intersect B is in fact equal to the probability of A times the probability of B. So based on this, A and B are independent, okay? I know it doesn't make sense. No, it makes sense, but you have to think about it mathematically, not intuitively. Do the calculation. So, okay, building off of that, consider an event C, the card is a jack. Then A and C are disjoint, but not independent. Example 3. Well, you know what? Let's dig into that. Okay, let's stop the speed run real quick and just dig into that, because I think it's a profound thing. And also, the speed run will definitely be more fruitful as we get into statistics, but probability, I feel, has more interesting depth. And this is a core thing because a lot of it can be unintuitive. So let's think about this. And maybe this is me being slow-brained, but I don't think so. I think probability in its nature can be an unintuitive thing to grasp. So why is the probability that you get a king and the probability that you get a jack not independent? Why is that not independent? Because you would think, again, I cannot get a king and a jack in the same draw. Well, two sets A and B are independent if and only if the probability of, let's say, a king given a jack is equal to the probability of a king, which is not true, because if you get a jack, the deck now has 51 cards at most. So you've now changed the probability that you can get a king on the second draw. That is why they're not independent, because one draw changes the probability of the next, right? But A and C are disjoint. If you think about it as a Venn diagram in a 2D plane, the circle for draw a king does not overlap with the circle for draw a jack in the same way that the circle for draw a king and draw a jack could overlap with the circle for draw a diamond, right? So think about the overlap of the circles on a 2D plane is disjoint. But think about independence as the probability, the probability of one is affected by the event of the other occurring, right? So independence is the shift in probability due to an occurrence of another event, reverse that. Independence is no shift in probability due to the occurrence of another event. Disjoint is no overlap in the occurrence of one event aligning with the occurrence of another. So let A and B be two independent events on S, and probability of A equals 0.3 and probability of B equals 0.8. Find probability of A union B. Well, we know that they're independent. So That means that they might not be disjoint, but the probability of A affects or does not affect the probability of B. If A occurs, still the same chance that B could occur. So we know, because they're event, that the probability of their intersection is just the multiplication of the probability of A and the probability of B. However, that's not what we're being asked right now. We're being asked for the union. And again, as we mentioned before, if you do not subtract out the probability of their intersect, then when you take the union, if you just do the additive operation, you're going to count the intersection twice. So you need to subtract out the intersection. And you know, one thing I want to note here is that this might seem very, very simple and easy, and it really kind of is, but things are going to ramp up, okay? Just give the speed run some time. It's going to get harder. I promise you. So, are the sets A and C independent? Well, if I'm not cheating, all we need to know if A and C are independent is whether this theorem holds true. So, what's the probability of A? Let's start with that, right? We know, because we just found out, that the probability of A is 0.3. And, oh, you know what? No. This is a different question. All right, speedrun. I'm pressing the resume button on the speedrun. More than two sets. Definition: the sets A, B, and C are called independent if and only if probability of A intersect B intersect C equals just the multiplicand of all of them. Am I using that term right? The multiplicand. All right. Brief side quest. Let's find out what multiplicand means. Define multiplicand. A quantity which is to be multiplied by another. The multiplier. Okay, I did use it wrong. I'm glad I checked. Okay. The multiplication really is what I should have said, but multiplicand sounds smarter. This is not where we want to be. 2.5. All right. So, yes. So, these sets A, B, and C are called independent if the probability A intersect B intersect C equals probability of A times probability of B times probability of C. And the probability of A intersect B equals the multiplication. Probability of A intersect C equals the multiplication, and the probability of B intersect C equals the multiplication. Okay. So note, disjoint events do not imply independent events, vice versa. Most of the time we know independent from the real world questions, for example, roll a coin or dice n times. Then we can use one side of the property. If A1, A2 to AN are independent, then probability of A1 intersect A2 and so on equals probability of A1 times probability of A2 and so on. So how many of these examples do we want to do? Let's do two. So let's, which one looks more complicated? This one does. So players A and B toss a fair coin in order, right? Tossing a coin. You have two people, A and B, toss a fair coin in order. The first player to throw ahead is crazy. Flip ahead. First player to flip ahead wins and ends the game. What are their respective chances of winning? So intuitively, right, the first person to flip is going to have a higher chance, but let's just think this through without looking at the solution. How do we calculate their respective chances of winning? So we want the probability that we want to find the probability that A gets ahead. Let's say, we know that, let's say A goes first, right? The probability that they get ahead is 1/2. Now B is going to go. The probability that B gets ahead is 1/2. But the probability of A getting ahead now on the next one is again 1/2. And then again, the probability of B getting ahead is 1/2. So the way my brain thinks about this is sort of like taken to the limit, right? It's gonna have an even chance each time. But on that first flip, B does not have a shot at winning, but A does have a shot at winning. So I kind of intuitively know the answer. I don't think I cheated. Maybe I saw this out of the corner of my eye, but I feel like it's 2/3. I might be dead wrong. I have no idea. I think I have some idea. I know that A's probability, whoever goes first is going to have a higher chance. But you know what? Let's actually solve this one. I feel like we can do it. So, what do we know? We know that since these events are independent, we can use one side of this property right here. So the probability of A1 intersect A2 intersect AN is the probability of A1 intersect probability of A1 times probability of A2 times probability of AN. So if we are looking for the probability that A will not get ahead, right? You have 1/2 times 1/2 up to 1/2. Probability that B will not get ahead is again 1/2 times 1/2 times 1/2 and so on. This is the type of question on a test where I would just write the answer and just write a bunch of, like, exactly everything I'm saying right now. I would try to mathematize it as much as possible and then just kind of just write the answer. But let's see. Okay, this is the point of studying. Let's walk through it. Okay, yes, I was right. But how do they get there? So, turns A, B, A, B, A. Player A wins if first head occurs on the first toss, third toss, fifth toss. I see here. So you have to enumerate the events. So probability that A wins is what we're looking for, not the probability that they necessarily get aheads on each flip. And you think about it not in terms of isolated events, but you think about it in terms of, this joint game that's going on, right? You see how I get stuck in a mental rut if I focus on A is doing this, B is doing this, A is doing this, B is doing this, instead of the sequence itself. So if A goes first, you have the probability that A wins equals PH plus PTTH plus PTTTH, and you're going to get 1/2 plus 1/2 cubed plus 1/2 fifth, right? Because T and H have the same probability. And that is going to simplify if you remember geometric series, which I totally remember geometric series. Sum to infinity AR K minus 1 equals A over 1 minus R if absolute value of R is less than 1. Who doesn't know that off the top of their head? Probability that B wins equals PTH, which is 1/2 squared, plus PTTTH, which is 1/2 to the fourth. So yeah, you just see this series and you use the geometric series rule, and now you got your answer. So I don't know if my teacher is sadistic enough to put this on the test. She just might be. You know what? She just might be. In which case, I'm going to have to take a little screenshot of this to make sure that I remember to write down the geometric series rule on my water bottle when I cheat. Totally joking. We get a note sheet. It's not cheating, it's a note sheet. It's allowed. I think I'm valid to admit that there were some times in high school where I had to come up with some very ingenious ways of figuring out how to cheat on math tests. I know, it's terrible. But the rubber band, I don't know if anybody else do the rubber band trick, but if you stretch out a rubber band and you write the stuff on the rubber band, then when you put it on your wrist, it just looks like scribbles. You can't see it. But if you're taking the test, I shouldn't be saying this, so I'm not going to say it. All right, so let's continue. Circuit problem, we don't need to worry about that right now. Example 9, roll a unfair biased coin 9 times or roll 9 coins once. Suppose the probability of getting head is probability of H equals P equals 1/3. So find probability that you get all heads. So rolling an unfair biased coin 9 times. That's just 1/3 to the 9. Yeah. And then probably no head, 2/3 to the 9. Okay. Exactly one head. 1/3 times 2/3 to the 8. Makes sense. But there's a choose in there because there's several ways there's 9 ways. Yes. Because it could happen at any point in the sequence. So you have to remember to multiply that by 9. Important thing to note. I think now is the point in time where, as the complexity starts to increase a bit, you're going to see me taking a lot of these screenshots so I know what to refer back to later. It's just a little pro tip for you out there. Take that, use that. Okay. But yeah, I also just want to explain why you see me doing stuff that's not on screen. Your boy got 2 monitors. Get like me. So, all right, we made it out of 2. Let's go. Now we're on to chapter 3, section 2, binomial probabilities. So for review, example, roll a biased unfair coin 8 times. Suppose the probability of getting head is P of H equals P. Find probability exactly 3 heads. We know that the result is 8 choose 3 times P to the 3 times 1 minus P to the 5. Reason, there are 8 choose 3 possible outcomes that have exactly 3 heads. Because again, we're rolling a coin 8 times. And we're looking for the probability of exactly 3 heads. So of course, 8 choose 3. For each outcome, the probability is P cubed times 1 minus P to the 5th. Again, this is an unfair coin. If it were a coin, P would just be 1 over 2, which would mean 1 over 2, yes, and 1 minus P would be 1 over 2. So this is not, the exponentiation here has nothing to do with the biasness of the coin, sorry. It has to do with the fact that we're looking for the probability of exactly 3 heads. So that's P cubed. And all the other events, so 5 tails, is 1 minus P to the 5th. This can be generalized to a series of n independent trials with 2 outcomes, success or failure. The binomial distribution theorem. Given a set of n independent trials with 2 outcomes, and 3 probability of success remains the same for each trial, suppose the probability of success for each trial is constant P. Then the binomial probability equals probability of k successes in n trials equals n choose k times probability of k times 1 minus p. Sorry, I said probability of k. Let me say it again. The binomial probability equals probability of k successes in n trials equals n choose k times p to the k times 1 minus p to the n minus k, where n equals the number of all trials, k equals the number of all successes, and p is the probability of success. Remarks. Key for application. Find the correct n, k, and p. When n equals 1, the binomial distribution is called Bernoulli variable distribution, which is 2 possible outcomes and 1 trial. Yes. The assumption means that there are n independent trials, and each trial is identically the same distribution. Here, each trial is Bernoulli distribution with probability p. This assumption is called IID, identical independent distributions. I like to think of it as independent and identically distributed, but it's really a synonym. Note, Q equals 1 minus P equals probability of failure. And probability of S, which is the entire sample space, which is always going to be equal to 1. Here is the sum for k equals 0 to n choose k, p to the k, q to the n minus k. And our example, we toss a coin 3 times. The whole sample space is shown there. Let k equals the number of heads. Then k equals 0, 1, 2, 3. And the sum, k equals 0 to 3, is 3 choose k times p to the k times 1 minus p to the 3 minus k. It's going to be equal to 1. See, this is fun stuff, right? Fun stuff. Let's skip this one. You know what, my motivation app just, I don't even like that motivation. I'm not even gonna read it off. So we're gonna skip this. How we feeling? Let's read one of these. Let's read example 3. So there are 100 marbles in a box, 60 red, 40 other colors. Choose 5 with replacement. So we already know that with replacement means we're going to be doing a binom, right? No, we don't know. I just read that. Choose 5 with replacement, which allows us to have independent trials. Okay, that makes sense. So binomial probability. Find probability of 2 red. So x is the number of red. X fits the binomial distribution with n equals 5. And p equals probability of red equals 60 over 100 equals 0.6. This makes sense, right? Again, X is the number of red. X fits a binomial distribution. N equals 5 because we're choosing 5. P equals probability of red is 60 over 100 because we have 60 red and 40 other colors. Here with replacement is necessary to make sure X is binomial. Compare with the next question. So trying not to cheat. We're asked to find the probability of 2 red and it's binomial. So we're choosing 2, right? So we have 100 choose 2. And the probability, so P to the K here, is going to be 6 over 10 to the 2 times 4 over 10 to the 3. Final answer. I'm locking it in. 5 choose 2. Yeah, 6 tenths to the 2 times 4 tenths to the 3. Cool. Choose 5 without replacement. Did I say 100 choose 2? I definitely did. Just ignore that. Choose 5 without replacements. Find probability 2 red. The probability that the first ball is red is 60 over 100 equals 0.6. Because there is no replacement, once we get the first red marble, the probability of getting the next red marble is changed. For example, probability of red, other equals, so 60 over 100 times 59 over 99 times 40 over 98 times 39 over 97 times 38 over 96. But if we change the sequence, in effect, these all become the same thing. It's really just 60, 59, 40, 39, 38. See this, this 60 matches with this 59 over 99. Huh, that's interesting. I mean, it makes sense intuitively, but it's cool that it does make full sense intuitively. I honestly feel like when you see it like this, it makes it feel a little bit more confusing. But maybe that's just me speed running this and not actually thinking. My brain is like turned off right now, but it's okay. Let's put it back on. Let's learn. There are 5 choose 2 possible outcomes with exactly 2 red marbles, and they all have the same probability. So the probability of 2 red is 5 choose 2, and then this long little number right there, this fraction right there. The general distribution for this question is called hypergeometric distribution. And are we going to get to the theorem for that? Yeah, we are, but we'll wait on it. Or will we? No, we just wanted to read that one example. Is any of this useful? You can use calculator TI-83, TI-84 plus to verify the calculation. So second, vars, a binom PDF. Probably important for me to remember. Let me zoom out a little bit. Whoa. You guys saw that? Or is it just me? The text is not in sync with the page. Let me, ah, damn. That's never a good feeling when you miss it. And now your screenshot folder is just clunked up. Okay. Cool. Just to see what I'm talking about, and I'm not crazy with the text not being synced with the page. Where was I? Oh, I totally am crazy. Okay, good to know. So, hypergeometric probability. Suppose a set population consists of n items, k of which are successes, and n minus k of which are failures. If we randomly select n items without replacement from a set of n items, of which k of the items are of one type, success, and n minus k of the items are of a second type, failure, then the hypergeometric probability is probability of x successes equals k choose x times n minus k choose n minus x over n choose n. Big N choose little n. So, way to think about this. You have big N total items, choosing little n from it. And then there's two sections. You have K, which is your successes. You got X of those. You're choosing X out of your successes. And you have big N minus K, which are your failures. And you're choosing N minus X out of them, because you're choosing N in total. Select N items, so small n items out of big N items with X successes and N minus X failures. I'm just going to repeat this again to really let it sink in. This is the definition of hypergeometric probability. Suppose a set population consists of big N items, K of which are successes, and big N minus K of which are failures. If we randomly select N items, little n items, without replacement from a set of big N items of which K of the items are of one type, success, and big N minus K of the items are of a second type, failure, then the hypergeometric probability is probability of X successes equals K choose X times big N minus K choose little n minus X over big N choose N. So, once again, going to take a screenshot. Actually, no, I don't want that. Screenshot all of this. Cool. Put it in my notes. And now, moving along. You know what song just popped out in my head? I'm not even going to say it. Don't worry. Example 1. Suppose we randomly select 5 cards without replacement from an ordinary deck of playing cards. What is the probability of getting exactly 2 red cards? So let's not even cheat. It's no cheating. Because we have this right here, which is all we need to know. We randomly select 5 cards from an ordinary deck. So we know that big N here is going to be 52 and little n is going to be 5. What's the probability of getting exactly 2 red cards, i.e. hearts or diamonds? So there are 26 red cards in our 52 card deck. So K is 2, right? Well, there's K successes, no. So K is 26. X is going to be 2. And big N minus K is going to be 26 as well. I wish I had a drawing tool here. Can I just get a drawing tool real quick? Is there an extension for that? This would make my life way easier right now. Web paint tool. Thanks, pass me. So, where were we? 3.2? Yeah. Let me turn on my web paint tool. How do I activate you? Oh my gosh. How do I activate you? Give me the command. This is, oh, okay, cool. Oh, I see. You can't do it in full screen mode. Okay, it's kind of annoying, but it's okay. So what do I want? This is pencil. Do you have a brush? No? Okay. Color, let's go. Big red. And no transparency. Let's up the size. Yeah. Okay, so this is gonna work. What do I have to be? Okay, cool. So, okay, what do we have? This is funny. So we know that K of the items are of one type, success. Let's start at the beginning, right? What do we know? We know for sure big N equals 5-2. What do we also know? We know that X is going to be 2, right? I can't even see the problem anymore, so it's kind of screwing me up. It's really a tragedy that that this is interfering with this right now. Okay. I really can't activate it in here. Let me activate it in here. Come on. Wow. What a loss. How about, can I open this up in a new, okay, you know what? I'm abandoning this whole terrible idea. It was a good idea, but it went wrong on me. It went bad on me. You know what I could do actually? Could I do this? Wow, the past me is really that guy. Oh wait, no he's not. I thought oh okay, he is, cool. So, come on. What? I have to be, I can't do my my split screen? Boy. Alright, separate these tabs. Let me, I guess I want to download the image. This is taking me so off topic. White screen, I'm just gonna go find an image. Yes, just open image, a new tab. Okay, just, you really couldn't make the white screen image bigger? Come on now. Is that big enough? None of these are big enough. How many, like, why do you have pixel restrictions on just white? And now it's just nothing? I mean, if this would stay, don't make changes. What is happening? I'm getting a virus. Come on. Just open in a new tab. Cool. Amazing. This is all I need. Now I just do this. Amazing. Cool. Okay, so now I can come in here. I should be able to. And open up my web paint tool. Awesome. Awesome, awesome. Cool, cool, cool. Okay. Now I can actually do math. So, where were we? Here's where we were. All right. Yeah. Okay. Let's make this. Oh no, actually this was the perfect. Yeah, that's perfect. What's the border line? Right there. Okay. So, and then zoom in. I don't. Okay. Cool. Sorry, this is taking forever. This is not the point of a speed run. So, but we're still speed running it. We're still going pretty fast. So, right, what are our variables here? We randomly select 5 cards without replacement from an ordinary deck. So it's an ordinary deck. We know n equals 52. All right. And we're selecting 5 cards without replacement. So, and what is the probability of getting exactly 2 reds? So, how many red cards are there? There's 26 red cards. So K is 26. And we're drawing 5 cards, so n equals 5. Yep. And so we know n minus x. Well, we got to calculate x first. What's our x? X is going to be 2, because we want the probability of getting exactly 2 red cards. So n minus x, 5 minus 2, it's going to be 3. And so to set it all up here, where's my, I have to see the pencil. So k choose x times n minus k, choose n minus x over big N, little n. And what that's going to look like for us is going to be 26, choose 2, 52 minus 26, which is just going to be 26, choose n minus x, which is just 3, and all of that over 52, choose 5. So it's really going to be, all this is going to be a travesty if this is incorrect. I'm not going to run my calculator right now because we can see if it's correct. But let's see. 26, choose 2, times 26, choose 3, over 52, choose 5. Beautiful. So, all right, we spent enough time on this. Let's go to 3.4. I'm going to keep this around. I hope it's a good idea. It might be a terrible idea. How do I, yeah, let's split these. Because it's defeating the purpose of the speed run a little bit, but it's kind of fun. This is the whole purpose of speed running, studying is just fun. That's the same reason I'm streaming this right now. I don't care if anyone ever sees this. It's just fun. It makes it more fun. And yeah, so, okay. 3.3 discrete random variables. Oh, but don't cut off the page. Cool. Denoted by X or Y. Motivation example. Toss 2 fair 6-sided dice. What is the probability? You know what? Ah, man, you're going to hate me. All right, let's get through this and then I'm going to take a little. Wait. How many pages? This is, how important is this section? It's a pretty important section. So I'm going to take a pause real quick and come back. I might cut this out of the video or I might not care and you might have to skip ahead. I apologize either way. But yeah, quick break. You know what's really sad? When I do that and forget to turn the microphone back on. That has happened to me several times when I'm doing paper readings. And it's always tragic because a paper will take like several hours to read, especially to try to read it out loud and explain, and maybe not even explain, just to read it. Yeah, but I remember to turn my microphone back on and we're good. So, discrete random variables. Motivation example. Toss 2 fair 6-sided dice. What is the probability that the sum of the numbers equal to 9? So we're looking for the sample space S has 36 sample points given by all of this and all of the events in which the sum of the numbers equal to 9 are this diagonal right here. So it's just 4 over 36. Makes sense based off of what we know. In this example, we only care about the sum of two numbers, so we want to redefine the sample space S to a smaller sample space in R using a random variable x, assigning each outcome a real number. So x such that S maps to the real numbers. A function that assigns a numerical value to each outcome. In our example, we define x such that a, b maps to a plus b. As a set x of S equals 2 to 12, a subset of the real numbers, which is called the range of x. If the range of x is a countable subset of R, then x is called a discrete random variable. For every discrete random variable x, we define a probability density function or mass function. And this is, I just want to say something here, okay? I'm going to get on my little soapbox. This annoys me. It's a probability mass function. Probability density function is for continuous variables. Soapbox tucked away now. But my teacher just calls it PDF, and this was really confusing to me when I first started learning this, because I would go look up things online, and it would just be like, what are you talking about? Probability density is continuous. Probability mass is discrete. It's fine, though. I get it. I get why she does it. It's okay. I just wanted to say that because it annoyed me at first. But probability x of k equals px of k equals the probability that x is equal to k, which is p of the set s, small s within the sample space, given x of s equals k. This is really a very much circular way of defining it, right? This colon equals is just saying this is literally what this is. But you just have to think about, really, this is the thing. Probability that x equals k. Pxk is a function from R to R. If k is not within x of s, then px of k equals 0. Question, find probability px of k for all k. In our example, the probability px of k of each number k in the range is assigned by px of k. So the probability that the numbers sum to 2 is only going to happen when you get 1 and 1. The probability that the numbers sum to 3 is only going to happen when you get 1, 2, or 2, 1, and so on. And you get the probabilities for each value of k, which k is just the sum. And this, all of this is the PDF. The probability that the sum of the numbers equal 9 is given by px of 9 equals 4 over 36. What is the probability that the sum of the numbers are less than or equal to 4? You just add all of them up. So px equals 2 plus px equals 3 plus px equals 4. And this is the cumulative distribution function or density function. Fx of t equals probability that x is less than or equal to t. In our example, okay, it makes sense. Remember, I'm doing a speed run. This is important though. Binomial distribution. Let the random variable x denote the number of successes in n independent trials. Then the binomial distribution can be stated as binomial prob, PDF. Sorry, you know what? I'm just getting annoyed by this white space here for no reason. I'm going to separate that. Close some of these tabs. Let's close this out so we feel like we're making progress, which we are. All right. I might start going faster. Speedrun isn't quite speedy enough for my taste. So, binomial prob, PDF, p x equals k equals n choose k times p to the x times 1 minus p to the n minus k. The cumulative distribution function of x, p x is less than or equal to t equals the sum from k equals 0 to t, n choose k times p to the k, 1 minus p to the n minus k. Theorem, necessary and sufficient conditions for a function to be a PDF. For a discrete random variable x. For any discrete random variable x, the PDF satisfies probability of k is greater than or equal to 0, and the sum for all k within x of s is equal to 1. Same thing as probability of the sample space is equal to 1. Okay, making sense, making sense. The definition of the CDF function is calculated by the sum of the PDF functions. We can also calculate the PDF using the CDF by the following proposition. For any discrete random variable x, the CDF function fx of t and the PDF function px of k satisfy px of k equals fx of k minus fx of k minus 1. Makes sense. Speedrun, speedrun. Speedrun. 3.4 Continuous random variables. The range of a continuous random variable x is a piecewise continuous interval of R. Motivation example. Choose a real number randomly from the interval 0, 2 sample space. If we assume the numbers are equally likely, we have the following probabilities. Px less than or equal to 2 equals 1. px less than or equal to 1 equals 1/2, and so on. Probability that x is less than or equal to x is equal to x over 2. S is a continuous set. There exists infinitely many numbers. Pick one number out of infinitely many numbers. Its probability is 1 over infinity, which is 0. We can continue this, and probability x equals 0 equals 0. In fact, probability that x equals a equals 0 for any real number, so we care about the probability for an interval. Again, this is for continuous random variables, not for discrete. Necessary and sufficient conditions for a function to be a PDF of a continuous random variable. So fx of x is greater than or equal to 0, and the integral from negative infinity to infinity of fx of x dx equals 1. That's the sample space. We also define fx of x equals 0 if x not in the range of x. So the probability that continuous random variable x is in an interval a to b is probability a is less than or equal to x less than b equals probability a less than x less than or equal to b equals probability of a less than x less than b equals probability a less than or equal to x less than or equal to b, because these are all the same because there's no real true points in a continuous space. And all of this is equal to the integral from a to b of fx of x dx. This is the area of the region from a to b. The cumulative distribution function of a continuous random variable x is just the integral negative infinity to x fx of t dt. So this bad boy right here. From the fundamental theorem of calculus, we have the relationship between CDF and PDF. Theorem: f prime x of x equals fx of x. Proof: fx of x equals the integral from negative infinity to x ft dt. F prime x of x is just d dx of integral negative infinity to x ft dt, which is just fx of x. We can use the CDF to find the probability. Probability a less than or equal to x less than or equal to b equals fxb minus fxa. So this is just everything up to b minus everything up to a is going to get you the area of the interval between a and b. Okay. Skipping. Cool. Important to note, uniform distribution thing. It's good to know, but I know it. And yeah, are these just all examples? Yes. Okay, cool. Made it through that. On to expected values. This is fun. You having fun? Okay. Expected values, long run average. I don't even know what that means. Expected value is a generalization of the concept average. Okay. Definition: expected value of discrete random variable. If x is a discrete random variable with probability function px of k, then the expected value or mean of x is expected value of x equals the sum for all k times px of k. This is straightforward. Proposition: expected value of ax plus b equals a times the expected value of x plus b. More generally, expected value of ax plus by equals expected value equals a times the expected value of x plus b times the expected value of y for RVs x and y. Straightforward. Theorem: expected value of binomial distribution. Suppose x is a binomial random variable with parameters n and p. That is, px of k equals n choose k times p to the k times 1 minus p to the n minus k, and the expected value of x equals np. Cool. Definition: expected value of continuous random variable. Expected value of x equals integral from negative infinity to infinity x times px of x dx. Cool. Definition: let x. So sometimes the mean is not enough. Honestly, my teacher never really tests us on the median, but I'll read it here. Let x be a discrete random variable. The median of x is the number m such that probability that x is less than or equal to m is greater than 0.5, greater than or equal to 0.5, and the probability that x is greater than or equal to m is greater than or equal to 0.5, so just the middle number. Cool. And the median of a continuous random variable is just the integral from negative infinity to m, fyy dy equals 0.5. Variance measures how far the data are spread out from the mean. The expected value of g of x equals the sum x within S of g of x times the probability x of x if x is a discrete random variable and the integral from negative infinity to infinity g of y times fy of y if y is a continuous random variable. In particular, we care about the case when g of x equals x squared. Warning, e of x squared is not equal to e of x squared. Calculate e of x squared for the random variable x in example 2. So you're just squaring all of these, and you're going to get expected value of x squared is 6. So again, it's, what am I looking at here? G of x, so 6 over 36, because that's just 6 over 36 times 0 squared, plus 10 over 36 times 1 squared, and so on. You getting it? You just square the x. Definition: the variance of a random variable x is variance of x is the expected value of x minus mu squared. Better way to think about that is the expected value of x squared minus the expected value of x squared. The standard deviation is the square root of the variance of x. This is the mean of the squared distance from the mean. It measures the spread of the data. Let x be a random variable. Okay, that's just repeating what we said. These are examples, very straightforward for calculating the variance. Okay, variance of ax plus b equals a squared times the variance of x. B goes to 0. The variance of a constant is 0. Let x be the binomial random variable. So x is from a binomial distribution, NP. Variance of x equals np times 1 minus p, which makes a lot of sense, equals npq. The standard deviation of x equals square root of npq. More about exponential random variable. Let x be an exponential random variable with PDF given by fx of x equals lambda e to the negative lambda x for x greater than or equal to 0, where lambda is a fixed positive integer, positive number. In section 3.4, we verified that it is a PDF with CDF, fx of x equals 1 minus e to the negative lambda x. In 3.5, we computed the mean of x, which is e of x equals 1 over lambda. In section 3.6, we computed the variance of x, which is variance of x equals 1 over lambda squared. And the standard deviation of x equals 1 over lambda. This is a very useful random variable to model the lifetime of some objects, i.e. computer parts, electronic equipment, etc. Geometric distribution. There is a discrete random variable that works similarly. For example, if we flip an unfair biased coin with probability head equals p, let y denote the times flipping until we get our first head. The PDF of y is probability py of k equals 1 minus p to the k minus 1 times p. The mean of y is 1 over p. Okay, recall geometric series, uniform distribution, stepwise function, fx of x equals 1 over b minus a for x within the interval a to b, and 0 for others. It's uniform distribution, same probability anywhere in this interval, otherwise no probability. Find the expected value and variance of x. You do this. You do a lot of stuff here. Okay. Moving to 3.7. Dismiss that. Joint densities for RVs x and y. Example 1. Toss 2 fair 6-sided dice. Let x be the difference of the two numbers. Let y be the larger number of the two numbers. The sample space S has 36 sample points given by all of that. From section 3.5, the range of x is x of s equals the set 0, 1, 2, 3, 4, 5, and the PDF of x is that right there. Similarly, range of y is y of s equals 1, 2, 3, 4, 5, 6, and the PDF of y is that right there. Discrete joint density. Let S be a discrete sample space. Let x and y be two random variables on S. The joint probability density function, joint PDF of x and y, is denoted by pxy of xy, defined as Pxy is the probability x equals x and y equals y. Theorem, necessary and sufficient conditions. The joint PDF has to be greater than or equal to 0, and the sum for all x and the sum for all y of the joint PDF is equal to 1. So if we're asked to find the joint PDF of x and y, then we're going to calculate this. X equals 0 and y equals 1 is going to happen 1 out of 36 times, right? Okay, we're gonna push through. We're gonna push through. Okay, so what's going on here? Why is it the case that x equals 0 and y equals 1, 1/36 of the time? We know that x is going to equal 0, 6/36 of the time, because x is the difference. Y is going to equal 1. The range of y, what is y again? Y is the larger of the two numbers. So how often out of 36 will the difference equal 0 and will the larger one equal 1? Well, that's only going to happen for 1, 1. Okay, this makes sense. And you just extrapolate that logic and you add all these up. Add up all the cases where x equals 0 for each value of y, and you get the marginal PDF for x is going to be 6/36, and so on and so forth. And yeah, you can do the same for the y, for the rows, and all of this is going to add up to 1. But the important thing to take away here is that these marginal PDFs are taken, so the marginal PDF for y is taken by holding this value of y constant and summing up what that value is for all of the values of x, and vice versa for the marginal probability of x. Theorem, let the joint probability be the joint PDF of x and y, then probability of x. Okay, this is just reiterating the marginal PDF thing. Yep. Find the marginal PDFs. Okay, so two random variables x and y are called independent if and only if the joint probability, the joint PDF is equal to the marginal, the probability of x equals x times probability y equals y. And then the definition for continuous random variables, joint probability is greater than or equal to 0. And again, just switch out the sums with integrals, and it has to equal to 1. The probability that x and y are in a region R in the xy plane, R squared, is given by this right here. So double integral fx, so double integral of the joint probability dx dy. And the marginals, same idea, single integral. So the marginal fx of x is the integral over y of the joint probability density function. And the marginal of y is the integral over dx of the joint PDF. And these are a bunch of examples. Let's get to the theorems. This is just the joint uniform density function. So this is the PDF for a uniform distribution. The joint uniform density is going to be K if x is within AB and y is within CD. So if x is within here and y is within here, then the joint uniform density is a constant because it's uniform. Makes sense. Theorem. Continuous random variables are independent if and only if there are functions g of x and h of y such that the joint probability density function equals gxhy. Cool, cool. Okay. Double integrals, this is just Calc 3 review. This is not very relevant. All right. So, you win some, you lose some. Do I want to do section 3.9? No. Will I do section 3.9? Yes. 3.9, further properties of the mean and the variance. So the expected value, so we talked about this earlier, and x and y are independent. If x and y are independent, then the expected value xy equals expected value of x times the expected value of y. If x and y are independent, then the variance of ax plus by equals a squared variance of x plus b squared variance of y. In general, the variance of ax plus by is going to be the same thing above, except you have to add 2ab times the covariance of xy. But if they're independent, then this is going to be 0. Here, covariance xy is the covariance of x and y, defined as the expected value of xy minus the expected value of x times the expected value of y. And if x and y are independent, then the covariance of x and y equals 0, because expected value of xy equals expected value of x times the expected value of y. So this is all straightforward, and I'm getting happier that I read it by the moment, because this is actually a very easy section to comprehend. Suppose random variables x1, x2 to xn are independent and each xi has the same distribution. Consider the sample sum, which is the sum x. Just add up all the xi's, and the sample mean is x bar, which is the sample sum over n. So x1 plus x2 all the way to xn and divided by n. Simple stuff. Covariance, and then there's the correlation, which is the covariance over square root of variance of x times variance of y, which could also be phrased as covariance of xy over the standard deviation of x times the standard deviation of y. That is the correlation of x and y. The correlation is the normalized version of covariance. A positive correlation or covariance means that y increases when x increases, while a negative correlation means that y decreases when x increases. Cool stuff. All right. I don't think it'll be fruitful for me to continue to what am I talking about? Of course it'll be fruitful. Push. This is a speed run, all right? But wait, my professor delayed teaching us 6.4 until later. Did I? Yes, okay. So I just finished 3.9. So now let's talk about some distributions. These I'm gonna go super quick through the rest, because I'm very, like, this stuff is way fresher in my mind because I've just been tested on this stuff recently. So, and it's also, in my opinion, sort of easier to calculate distributions. Actually, it's not even really a subjective thing. It's very easy to bust out a calculator and figure out a normal distribution or a Poisson, whereas the integrals of a lot of this stuff in chapter 3 are, in my experience, some of the easier places to get lost. The only other place where it's easy to get lost for me is just doing the algebra of maximum likelihood estimation, and like, yeah, it's just easy to get lost in that algebra. But most of the other stuff that we're going to talk about here is actually pretty simple, so I'm just going to breeze through it. So, Poisson distribution, yeah, this is just, with the binomial, our random variable x was the number of successes out of n trials of an experiment. The Poisson distribution counts the number of occurrences per unit of measurement, for instance, a specific period of time or in a specific area or volume. So this is the function. Poisson discrete, lambda to the k, e to the negative lambda over k factorial. The expected value of x is just lambda, and the variance of x is just lambda. And the Poisson approximation for the binomial, it's a pretty good approximation. Just if n is large and p is small, then let lambda equals np. And yeah, how to determine lambda? Np equals lambda equals the average number or rate of occurrences per unit times the length of the observation period in unit time. And this is how you do it with the calculator, which makes all this stuff pretty simple. And yeah, so normal distribution. standard normal distribution. This is the function. Don't really need to remember it, but you need to remember 0 mean and 1 variance. And this is what it looks like. It's a Gaussian. It's a normal distribution. And probability that a is less than or equal to z, less than or equal to b, equals the integral from a to b, fz of z dz, which is just normal CDF on a calculator. Simple stuff. And yeah, this is really where the calculator takes over. If you want to find the pth percentile, you just use n of norm. And this is a non-standard normal distribution. Pretty much just teaches you how to set it up when the mean is anything but 0 and the variance is anything but 1. What you're going to want to do is you're going to want to normalize it. So x equals the mean plus the standard deviation times z. Another way is z equals x minus the mean over standard deviation. This is really what you want to remember here. And yeah, simple, easy stuff. Central limit theorem, again, remember sample sum and sample mean. So pretty much all this is saying is if your number of samples is greater than or equal to 30, just make it normal. Just assume it's normal. And x bar comes from a normal distribution, mu sigma squared, so that's the variance over n. And yeah, the sample mean, so CLT as a standard normal distribution, sample mean x bar minus mu over sigma over square root of n comes from a standard normal. And sample sum, x minus n times mu over sigma times square root of n comes from a standard normal. Yep. Do I need to remember this? Of course I do, but do I need to review this right now? No, it's pretty straightforward. CLT for sample sum. Pretty sure that's just another way of saying this. Pretty sure. Not 100%. I'll read it. X comes from n mu n sigma squared. Cool. And yeah, so more precisely, as n approaches infinity, the probability a less than or equal to z, which is just x bar minus mu over sigma over square root of n, less than or equal to b, equals the integral. It's just the PDF for z. And yeah, simple stuff. Approximating binomial with the normal. Just make sure you do continuity correction. That's all it comes down to. Cool. And yeah, trying to remember, my teacher did this in a interesting order, and I'm just trying to remember what order I should review it in so that my brain makes the most of it. But actually I do have the order screwed up here. So real quick, just an aside, I'm training this model right now in this Jupyter notebook, and it's going super slow, but it's fun. It's just fun to train a model and just doing. It's at 16%, not terrible. And this is GPT-2 large, so it's been baking for a while, as you can see. It's been going for a minute, and excited to see what the loss looks like when it's done. So, okay. So, 5.2, parameter estimation. Okay, this is just the maximum likelihood. You just got to do this. Just follow this sequence of steps. You take the product of the PDF, and then you take the natural logarithm of what you get, and then you take the derivative of that with respect to theta, and you solve for theta. It's really actually very simple. It's just the algebra that can get tricky, especially when it comes to figuring out how to distribute certain exponents when you're doing this, when you're rolling out the product. But it's a simple concept. And 2 parameters, literally the same thing. Biggest difference is just that you gotta calculate the partial derivatives for the 2 different parameters. Cool. And interval estimation. Point estimation. Any point estimator is a random variable whose distribution is induced by the distribution. Okay. Main takeaways from this section are confidence interval, which is very easy. It's just the population mean plus or minus the, what is it called, the z-score? Z alpha over 2. All of this is the error. It's not the z-score. It's something. What is this called again? Critical value? Okay, don't mind me. But yeah, it's just an error, a plus or minus from the population mean. And confidence interval for estimating a population mean mu with sigma known, z alpha over 2. Oh, the critical value, yeah. So yeah, the population mean plus or minus critical value times the standard deviation over square root of the number of samples. And you can use inv norm to make this pretty simple to calculate the critical value. And once you have the critical value, this is all pretty simple. Except there was this test I took where we were not given the standard deviation, but we were told that the standard deviation is known. I wonder if there's the answer to how to figure that out here. I'm not going to do it right now because I have plenty of time to my test. This is just the speed run review, but something to be aware of. Okay. Confidence level is just 1 minus the alpha. Alpha is the level of significance, and sigma over square root of n is the standard error. And when you multiply that sigma over square root of n times the critical value, you get the margin of error. And if you double the margin of error, you get the length or width of the confidence interval. And you can calculate finding the confidence interval for estimating a population mean with sigma known, same thing as above. And yeah, calculator is the interval is why this is pretty easy in practice. And it's actually all easy, even without a calculator. Like you just do some simple algebra. It's simple. Finding a sample size for estimating a population mean, pretty straightforward. You just gotta figure this out. Just do this algebra. Just plug in the critical value times the standard deviation over the margin of error and square it, and make sure that you round up. That's all you gotta do. Okay, the z-score is the same thing as the critical value, so I was right in both ways. Cool. So okay, these are some common choices for alpha, so you don't have to type it all out. 5% alpha, okay, simple. Well, I'll finish my sentence. 5% alpha is 1.96 for the z-score or critical value. This is all simple, and then population proportion p, confidence interval, so just p plus or minus the critical value times square root of p hat times q hat over n. It's the margin of error. One prop z int is how you do it easily with a calculator. Sample size n for estimating population proportion p. So if you have a p hat, which is just a proportion estimate, then you're going to need more than or equal to the critical value squared times p hat times q hat, which is just 1 minus p hat, over the margin of error squared. When no estimate of p hat is known, you just make this a quarter. And the way I think about it, which could be completely flawed, I don't know, but the way I think about it is, if you don't have an estimate for the proportion and you just assume that it's 50-50, then p hat times q hat becomes 0.25. My teacher didn't explain it like that. That's what makes sense to me. But we'll keep rolling. And these are all examples. Cool. So yeah, very simple section. Properties of estimators. An even simpler section. Just know that an estimator theta hat is said to be an unbiased estimator for a parameter theta if the expected value of theta hat is equal to theta. So all you do is you find the expected value of theta hat, because that's our estimator, so it'll be given, and then you see, is it equal to theta? If it is, you're good. If you're not, you're not. And yeah, these are some facts which really have not proven to be that relevant in any of my tests. But still good to know, honestly, especially for machine learning stuff. S squared equals the sample variance, and S squared is an unbiased estimator of the population standard deviation, or of the population variance, and S equals sample standard deviation. Yeah. So, okay, we're almost there. Hypothesis tests. These are pretty simple. You're going to do the z-test for the mean when the population standard deviation is known. You're going to do the z-test for the proportion. Again, I think when the population standard deviation is known. And the t-test for the mean when you don't know the population standard deviation and you only know the sample standard deviation. So you have a null hypothesis, which is what you assume to be true. You have an alternative hypothesis, which is what you're testing for. You calculate the test statistic, which lets you decide, which lets you make a claim, whether you should reject or accept the null hypothesis. You identify the critical values at a given level of significance. That's just the alpha. Identify the p-value, which is another way of sort of testing whether you should reject the null hypothesis, and then state the conclusion. After your test, it looks like this. If the alternate is testing for mu greater than your null hypothesis, your mu naught, then it's a right-tailed, and so on and so forth. If you're just saying if this is wrong, if you just want to test if your null hypothesis is wrong, you have a two-tailed test. Just mu is not equal to mu naught. And this is the way you conduct the significance tests. Z-test or t-test, proportion, z-test, simple stuff. I mean, simple for me because it's fresh in my brain, I know. But this is a speed run. Significance level, test statistic, estimate minus hypothesized value, standard deviation of the estimate. So z star equals x bar minus mu naught over sigma divided by square root of n. For t-test, t star equals x bar minus mu naught over s divided by square root of n. And you're going to want to do the z-test when sigma is known, and the t-test when sigma is unknown. And then test statistic for proportion, z star equals p hat minus p naught over square root of p naught times 1 minus p naught over n. Cool. Critical value, inv norm or inv t. And p-value, probability that z is less than or equal to z star, or probability that t is less than or equal to t star. And you're just doing the normal CDF for z or the t-CDF for t. And after you calculate that, if it's two-tailed, you multiply it by 2 for z greater than the absolute value of z star, and so on for t. And then you compare this to the p-value, you compare it to the significance level, to the alpha. If the p-value is less than or equal to alpha, reject the null hypothesis. If the p-value is greater than alpha, you fail to reject the null hypothesis. And that's just saying, like, is this statistically significant past my threshold? And if it is, then we accept our alternative hypothesis. And yeah, these are examples. These calculator functions make all this super easy. And yeah, just more examples. This is honestly the easiest stuff out of everything I've talked about so far. And then I know 6.4 is here, but my professor taught us 7.2 and 7.3 first. So let's just talk about this. The t-distribution, this is when the population standard deviation is not known, but you'll have a sample standard deviation, and that's s, and that's the square root of the sum xi minus x bar squared over n minus 1. Here, n minus 1 is your degrees of freedom. And these values are taken from a t-distribution, the critical values. And so when sigma is known, you're dealing with this non-standard normal distribution. When sigma is not known, you're dealing with this t-distribution, which are pretty simple. I mean, it's pretty similar. It's just you're swapping out the population standard deviation for this sample standard deviation. And you're going to need to use some degrees of freedom, the degrees of freedom, to calculate some sample statistic stuff down the line. And this is T, the one sample T statistic, just the sample mean minus the population mean over the sample standard deviation divided by the square root of your number in your sample. That's how you normalize it to just do the normal TCDF. Or TPDF, right? It's a thing, I think. Yeah, so don't worry about this. Main thing to remember here is that you can calculate your T alpha df equals the 1 minus alpha percentile of a T distribution with degrees of freedom df, such that the probability T is less than T alpha df equals 1 minus alpha, and probability that T is greater than T alpha df equals alpha. And you can calculate that with inv T, the function. As long as you know alpha and you know your n or your degrees of freedom, and remember degrees of freedom is just n minus 1, then you can calculate your inv T. And the confidence interval for the mean when the population standard deviation is unknown, your margin of error is just going to be this T alpha over 2 df times sigma square root of n. Not sigma, it's the sample standard deviation. But yeah, you're just doing this. This is your new margin of error now. And the critical value, yep. This is how you can normalize things. X bar minus the mean over the sample standard deviation divided by square root of n. And again, these calculator functions make all this very easy. If you have data, you use this. If you don't have data, you use this. And you can calculate this with T interval. Yeah, same thing. Cool. All right, one more section. And type 1 and type 2 errors, right? So there's different ways of getting things wrong. If the null hypothesis is true and we decide to reject the null hypothesis, this is a type 1 error. Rejecting a true null hypothesis. And the probability of a type 1 error is equal to R alpha. And if the null hypothesis is false and we reject it, that's a correct decision, 1 minus beta. If the null hypothesis is true and we fail to reject it, so accept it, that's a correct decision as well. I believe that's meant to say 1 minus alpha. And type 2 error is when the null hypothesis is false, but we fail to reject it. So failing to reject a false null hypothesis is a probability type 2 error equals beta. And so again, yep, alpha probability type 1 error, probability reject the null hypothesis given that the null hypothesis is true equals level of significance of the test. Power of the test is 1 minus beta equals the probability reject null hypothesis given that the null hypothesis is false. The confidence level is 1 minus alpha, and the beta is the probability of a type 2 error equals the probability of accepting the null hypothesis given that the null hypothesis is false. And this is an example. You just calculate it because you have your rejection rule, reject H naught if X bar is greater than 425, and probability that X bar is greater than 425 given that mu is 400. You do the normal CDF, so 425 and greater with a mean of 400 and a variance of 100 over square root of 50, or maybe that's the standard deviation. Either way, yeah, either way, you plug it in the calculator and you get the answer. Ah man, if you go back on some of the videos on this channel, you'll see that I've studied for like, I don't even know what my max is. There's been 8-hour streaks, and I'm just not feeling it today. Today's not the day. It's okay. I'm warming up. We're getting in. I have like 10 days to my final, so just warming up. It's okay. Don't update the software. Keep it old-fashioned. Keep it retro. So these are just more examples, and it's yeah, it's straightforward. You have some 2 types of errors. You're going to need some stuff for it. Your critical value, your rejection rule, and then you just do the conditional probabilities with a CDF. And yeah, you really just need the inv norm function and the normal CDF. It's beautiful. So yeah, I hope you enjoyed my TED Talk. There actually are some other modules. There's one more module remaining, technically, that the lecture notes are released for, but I haven't actually read it. So you know what? Let me just read it now. This will be me reading it as, for the first time, just with you. But I might as well do it because we're at the end. So, two sample inferences on mu1 minus mu2. 9.2 is a test for the difference between population means using the z-test or t-test. 9.5 confidence intervals for mu1 minus mu2. Comparing two means. Suppose you want to compare salaries between two companies. We will let mu1 equals mean salary from company 1 and mu2 equals mean salary from company 2. Since we want to compare these means, what parameter should we use? Intuitively, we could use the difference in means mu1 minus mu2. We can estimate this with the difference in sample means x bar 1 minus x bar 2. Two sample inferences on mu1 minus mu2. For known SDs, sigma 1, sigma 2, use z distribution x bar 1 minus x bar 2 comes from a normal distribution mu1 minus mu2, sigma 1 squared over n1 plus sigma 2 squared over n2. Assumptions. For the z-test or confidence interval to determine the difference between two means, both samples are random samples. The samples are independent of each other. Standard deviation of both samples must be known. If either of the sample sizes is less than 30, the populations must be normal or approximately normally distributed. Confidence interval x bar 1 minus x bar 2 plus or minus this margin of error, which is z alpha over 2 times square root of sigma 1 squared over n1 plus sigma 2 squared over n2, and the test statistic z star equals x bar 1 minus x bar 2 over square root of sigma 1 squared over n1 plus sigma 2 squared over n2. On calculator, two sample z-test or two sample z-int. So for hypothesis test, you use two sample z-test. For the confidence interval, it's two sample z-int. For unknown population standard deviations, use the t-distribution. So it pretty much actually is the same thing. Yep, same assumptions, except slightly different parameters. You're just going to use t alpha over 2df. And here, this is interesting. The test statistic is pretty different, but sort of the same in a obvious way, because the square root of 1 is just 1. So, yeah, you're using this function and you're using these calculator functions. If the population standard deviations are assumed to be unequal, non-pooled, then it looks like you take this standard deviation out of here and you just have unique standard deviations. Yeah. Okay. And you can do the tests, and this time instead of comparing total mu to a mu naught, you just compare the two different mu's to each other. The basic format for hypothesis testing: state the hypotheses and identify the claim, compute the test value, find the critical values or p-value, make the decision. Critical value and p-value methods are same as before. Okay, and now a bunch of examples. And you can input data and do the calculator function with the data. Step-by-step hypothesis test for the difference between two means and z-distribution. So you enter in the data, you do two sample z-test, and you just press enter a bunch of times. Same thing here, you just go to two sample z-test, you enter in your values, and you press enter. Confidence interval, if you have data, you enter in the data, two sample z-int, keep pressing enter. If you don't have data, two sample z-int, and you put in your values, you press enter. Oh my gosh, it's just a bunch of telling me how to type on my calculator. Alright, well these are just examples, so let's finish off with reading some lovely calculator functions, because who doesn't love to just use a calculator to answer a problem? Hypothesis test for the difference between two means and t-distribution. You're just going to go to two samples t-test, enter in your values, And on the line for pooled, move the cursor to no if it's not pooled. Whereas you're going to go through the same process, or no, this is a different process. Confidence interval for the difference between two means and t-distribution. To sample t-int, enter in your values. On the line for pooled, move to no. Standard deviations are assumed not equal, and you press enter. And then yeah, these are extra problems. But yeah, you literally just saw me go through every single of the lecture notes, except for these extra confidence interval examples, which are super easy and completely tied into what we talked about. So yeah, that was me just filling my brain with almost everything I'm going to need to know for my final test, at least on a high level. So now I'm going to have to actually go do problems and remember and review the math for real. But this was good. I'm glad I did this. So, peace.